In this video, we're going to be doing operations with radical expressions, different kinds. We're going to start off looking at multiplication and division. And multiplication and division requires the indexes to match, not the radicand themselves, but the index. So we've done this a little bit with multiplication. So to multiply radicals, they have to have the same index. So here we've got two cube roots. We've got the cube root of 5 times the cube root of 4. Since they have the same index, I can write them under the same radical symbol. And I have the cube root of 5 times 4, which is the cube root of 20. In this problem, they're not the same indexes. I have the fourth root of 7 times the third root of 10. Since I've got an index of 4 and an index of 3, I can't simplify that. And so the answer is the fourth root of 7 times the cube root of 10. And that would be it. To divide, they also have to have the same index. So here's two square roots that I'm dividing. The square root of 6 divided by the square root of 18. Granted, it looks like a fraction, but fractions is just one form of writing a division problem. Since they have the same index, I can write them all under one radical, then simplify that fraction, then break the fraction up because I notice the denominator can be simplified even more because I've got the square root of 9, and I have the final answer of the square root of 3 divided by 3. In this next problem, I have 7 cube root of 81 divided by the cube root of 3. Both of those radicals are cube roots, so I can write them under one radical symbol. And then 81 divided by 3 is 27, so I simplify that further. Knowing that the cube root of 27 is 3, I have 7 times 3, which is 21, which is our final answer. And next problem, both of these are fifth roots. So since they're both of an index of 5, I can write them all under one radical and then simplify that fraction, which is a type of doing part of the division. And I end up with, under the fifth root radical, I've got 32b cubed divided by a to the 10th. And I need to figure out how to simplify that. I need to know if there's a cube root for that. And the best way to do this is to write them in exponential form. So I know that 32 happens to be 2 to the 5th. And I had a to the 10th in the denominator. Well, a to the 10th could be written as a squared to the 5th. And so now I know that 2 and a squared can both come out, and I've got 2 divided by a squared, the fifth root of b cubed, and that is my final answer for that division problem. What we just did in that last problem is a type of simplification by factoring the radicand. And what we're doing when we're factoring that radicand is we're trying to find out if parts, meaning the factors, can be written in exponential form such that the exponent matches the index. And if you pause and go back in the video to the previous problem, you'll see how we did that with that last problem. But let's look at it more fully. It goes back to this rule. We're going to assume at this point that all of our variables are positive. We're not going to deal with absolute value bars here. So the nth root of a to the n is just a. And here's another example where if I had the nth root of b to the 2n, well, I could write that as b squared to the n. So now I've got the index of n, and I have this b squared raised to the n, so therefore it's b squared that's going to come out. So here we're going to simplify the cube root of 16. Well, we break it up so that we can think of factors that could be written to the third degree. And so we break up 16 to 8 times 2 because 8 can be written as 2 cubed. And so we have the cube root of 2 cubed times the cube root of 2, and that simplifies to 2 cube root of 2, which is our final answer. In our next problem, we have fifth roots, and we're multiplying. But since they're both indexes of 5, I can write them all under one radical symbol. And I happen to notice that 162 is 81 times 2. Now remember, I'm not going to actually multiply the 9 times the 162 because the goal here is to factor, to pull things apart. So I'm looking at how I can write these in factored form. And 162 is 81 times 2. And therefore I can say, oh, well, 9 is 3 squared, and then 81 is 3 to the 4th times 2. all under the fifth root. And so I've got the fifth root of 3 to the sixth times 2. Well, 3 to the sixth can be broken up, and 3 to the sixth can be written as the fifth root of 3 to the fifth times the fifth root of 3. And then I still have the fifth root of that too. And the fifth root of 3 to the fifth is just 3. And then since both of those radicals have the same index, I can put them under the same radical. And then simplifying them, I end up with 3 fifth root of 6. That's my final answer. In this problem, we have fourth roots. So we can write, and they're already factored form, which is kind of nice. It's sweet. So we write the fourth root of the following. I'm going to put them in order. I've got 2 squared. And it says 3 to the 15th. Well, that's because we had 3 to the 5th and we had 3 to the 10th. And we'll add our exponents when you're multiplying like bases. So I get 3 to the 15th. And then again, I have x to the 16th because I had x to the 7th and x to the 9th. I'm looking for ways to break them up into, so I can write them with exponents of 4. And I broke up that 3 to the 15th to 3 to the 12th times 3 to the 3rd. The x to the 16th, I saw, oh, well, that could be x to the 4th raised to the 4th. But why did I break this up to the 12th? Because 12 is a multiple of 4. I'm looking for that index of 4. I'm looking at how I can write this exponent as a 4th degree. And I note that 3 to the 12th could be rewritten as 3 to the 3rd to the 4th, which means the 3 to the 3rd and the x to the 4th can come out. So I've got 3 to the 3rd, x to the 4th, and then what's left behind under the radical, the fourth root is 2 squared and 3 squared. Our final answer should not be left in this exponential form. We should figure out what these all are. So we notice that 3 cubed is 27. And then we have 4 squared times 3 cubed. Well, that's 4 times 27, which is 108. So to finish this problem, we write it out as 27 x to the 4th times the fourth root of 108. And that is our final answer. And our last little section here is on adding and subtracting of radicals. And adding and subtracting of radicals is just a fancy way, we're just collecting like terms. We're saying how many of each type do we see. So here I've got 3 square roots of 14, and I have 5 square roots of 14. So I want to know how many square root of 14s are there. Well, 3 and 5 is 8, so I have 8 square root of 14s. This next problem, I have cube roots of 21. I have 6 cube roots of 21. I want to take away 13 cube roots of 21, and I have 5 cube roots of 21. Well, since I have 6 and 5, that's a grand total of 11, but I'm taking away 13. I want to know how many cube roots of 21 there are, and altogether that would be a negative 2 cube roots of 21. In this problem, we are collecting, we're figuring out how many fourth roots of 2x do we have. Well, we have negative 3 fourth roots of 2x, we have positive 8 fourth roots of 2x, and we have positive 4 fourth roots of 2x. So we can collect it in this manner, so we can see real clearly we've got negative 3 plus 8 plus 4 of the fourth roots of 2x. And when we finish that up, we get that we have 9 fourth roots of 2x. Sometimes when we're trying to collect these like terms, they don't look like they're alike. In problem number 4, I've got the square root of 12 plus the square root of 3, and say, well, we can't collect things because those aren't alike. But if we simplify, so the square root of 12 happens to simplify. It's the square root of 4 times the square root of 3, which is 2 root 3. And then we're still adding that root 3. So I have 2 root 3s and I have 1 root 3. And altogether, I have a grand total of 3 root 3s. So I could collect. I have to simplify first and then collect. In problem number 5, I've got 7 square root of 45 minus 2 square root of 5. And we notice that the square root of 45 can simplify. And so I have 7 times the square root of 9 times the square root of 5, which is 7 times 3 square root of 5, which is 21 square root of 5. And I'm still taking away 2 root 5, which is a grand total of 19 root 5s. In problem number 6, well, here we've got groups. I've got the square root of the group 25x minus 25. Both of those terms under that radical are divisible by 25. So both of those I could factor out of that radical, the square root of 25. And in the second, where I'm subtracting the square root of 9x minus 9, both of those terms under the radical symbol are divisible by 9, so I could factor out a square root of 9. And then the square root of 25 and the square root of 9 simplify, so I have 5 square roots of x minus 1, minus 3 square roots of x minus 1, and when I collect that all together, I end up with 2 square roots of x minus 1. In the last problem, we have cube roots. I have 2 cube root of 125 a to the 4th, minus 5 cube root of 8a. Well, in the first term, I've got the 2 and then the cube root. Well, 125 happens to be 5 cubed, so I know that a 5 will come out. A to the 4th, well, that can be written as a to the 3rd times a to the 1st, so a to the 3rd comes out of the cube root, so I end up with a and the cube root of a. This next one, I have the minus 5 and then the cube root of 8a. But the cube root of 8 is 2, so it comes out. And then the cube root of a, well, there isn't one, so it just stays there. Now I can simplify each of these, so the 2 times 5 times a gives me 10a, and then I have cube root of a. The second one, I have minus 5 times 2, so I have minus 10 cube root of a. Now look very carefully because there's more simplification to do in this problem. Both of these terms have a 10 and a cube root of a. So I could factor out the 10 cube root of a. And when I factor that out, what's left behind is an a minus 1. So this problem, the final answer, all simplified, is 10 cube root of a times a minus 1. Might want to pause or replay some of these and watch some of these examples several times because there's a lot that's in this video.